Hi, for this lecture I'm going to talk about registers. Okay, registers. Registers are high-speed memory locations inside the CPU. So this is your von Neumann machine architecture. So this is your CPU and this is your supposedly registers, but in von Neumann architecture the register there is represented by the accumulator. So it's still inside the CPU. Registers categories. So registers are grouped into three categories. You have general purpose registers or general registers, control registers, segment registers, and general registers are further divided into the following groups: data registers, pointer registers, and index registers. For data registers are used for arithmetic, logical, and other operations. Some of these data registers have specific use in arithmetical operations. AX is the primary accumulator. It is used in input, output, and most arithmetic instructions. For example, in multiplication operation, one operand is stored in EAX or AL register according to the size of the operand. And it's not mentioned here, but AX is also important for interrupt function calls, specifically AH, because that's what will determine what the interrupt will do, especially interrupt 21. So if you have interrupt 21H, you have to look at what's the value in AH to determine what will the interrupt will do. Okay, so BX is known as the base registers, as it could be used in index addressing. CX is known as the count register, as the ECX register store the loop count in iterative operations. DX is known as the data register. It is also used in input-output operation. It is also used with AX register along with DX for multiply and divide operation involving large values. So, like if you're going to display hello world, you usually use DX where you put your data. That's why one of the special use for DX is for data. Then you have pointer registers. Pointer registers are IP, SP, and BP. Instruction pointer. It's a 16-bit register that stores the offset address of the next instruction to be executed. IP in association with the CS register, as CSIP gives the complete address of the current instruction in the code segment. So when there is an interrupt, the CS and IP, specifically the IP, has to be saved somewhere, so that when after the interruption, when the CPU is ready to go back where it stopped, it can always point to the instruction that was not executed because there was an interruption. So it was taken care of by the CS-IP combination. And then you have the stack pointer. It's also 16-bit registers, provide the offset value within the program stack. SP association in association with the SS registers or SS SP refers to be supposedly to the current position of data or address within the program stack. And then you have the base pointer BP, still under pointer register. It's also 16-bit. Mainly helps in referencing the parameter variables passed to a subroutine. The address in SS registers combined with the offset in BP to get the location of the parameters. BP can also be combined with DI and SI as base register for special addressing. Then you have index registers. 32-bit index registers are used for indexed addressing and sometimes used in addition and subtraction. There are two sets of index pointers. One is source index or SI. It is used as source index for string operation. And you have destination index or DI. It is used as destination index for string operations. So you have the source index and you have destination index. Control registers. The 32-bit instruction pointer registers and 32-bit flag registers combined are considered as the control registers. So you have instruction pointer, IP, and flag registers. They become the control registers. So many instructions involve comparison and mathematical calculations and change the status of the flags and some other conditional instruction test the value of these flags to take the control flow to other location. So one of those flags is the overflow flag. It indicates the overflow of a high order bit, leftmost bit of data after a signed arithmetic operation. You have direction flag. It determines left or right direction for moving or comparing strings data. When the DF value is 0, the string operation takes left to right direction, and when the value is set to 1, the string operation takes right to left direction. To continue, you have the interrupt flag. It determines whether the external interrupts like keyboard entry, etc. are to be ignored or processed. It disables the external interrupt when the value is 0 and enables interrupts when set to 1. Then you have trap flag. It allows setting the operation of the processor in single-step mode. The debug program we use sets the trap flag so we can step through the execution one instruction at a time. So we will see this later on in our emulator. I'll have to take note of that. Trap flag. Sign flag. It shows the sign of the result of the arithmetic operation. This flag is set according to the sign of data item following the arithmetic operation. So there's a result is negative or positive. So if it's negative, there is a change in the sign flag. So we have there positive results clears the value of sign flag to 0 and negative result sets it to 1. Then you have auxiliary carry flag. It contains the carry from bit 3 to bit 4 following an arithmetic operation used for specialized arithmetic. The AF is set when 1 byte arithmetic operation causes a carry from bit 3 into bit 4. Still control registers. You have the 0 flag. It indicates the result of arithmetic or comparison operation. A non-zero result clears the 0 flag to 0 and the 0 result sets it to 1. So when you have like AX minus AX, the result is 0, so 0 flag will be reset. Or XOR AX AX, that's still 0, so again your 0 flag will be set to 1. Then you have parity flag. It indicates the total number of bits, 1 bits, in the result obtained from an arithmetic operation. An even number of 1 bits clear the parity flag to 0, and an odd number of 1 bits set the parity flag to 1. So then you have carry flag. It contains the carry of 0 or 1 from a high order bit after an arithmetic operation. It also stores the contents of last bit of a shift or rotate operation. So this is the location. If you have the flag register, this is the location. So the rightmost bit contain the carry flag. Here they have the parity flag. So this becomes 1 if the odd number of 1 here. Then you have the auxiliary. You have 0 flag. This is 0 if there is no 0 result, but it becomes 1 if the result of arithmetic is 0. Then you have sign flag. This becomes 1 if the result is negative, and then all the rest here. Okay, so now we have segment registers. Segments are specific areas defined in a program for containing data, code, and stack. There are three main segments. You have code segment, contains all the instructions to be executed. A 16-bit code segment. Register or CS register stores the starting address of the code segment. Data segment, it contains data, constant, and work areas. The 16-bit data segment register or DS register stores the starting address of the data segment. And then you have the stack segment, contains data and return addresses of procedures or subroutines. It is implemented as stack data structure. The stacks segment register or SS register stores the starting address of the stack. By the way, when you open your emulator, you will choose whether you are going to compile for a COM or exe. You will notice that if you will choose exe, there is an implicit you will implicitly not implicitly, sorry, you will explicitly define the different segments in your code. Actually, it is already predefined when you open an exe. But if you are only doing a COM, which what I am using in all the other examples that I have, you don't have to define the code segment, data segment, and stack segment. It is being taken care of by your operating system. So that's the difference. You have a COM, COM, .com, and .exe. So both of these are executable. But the segment, the management of the segment differs. One, you don't have to manage the segment. The other one, you really have to define the code segment, data segment, and stack segment. Okay, so before we go there, let's see some example. Okay, so I prepared something. So basically, this is these are the registers. The red, those that are in red are the registers. The blues are the instruction sets, the mnemonics. So basically, this will just, if you're going to run the program, you're going to run the program to just say hello world. What happened to my hello? Oh, yeah, I missed. There is something there because I deleted some value, but we can fix it. Wait, so that I will not affect the value. I'm going to remove it here. I'm going to put it here. There. Simulate, run again, just so you will see the hello world. Okay, there, the hello world. So basically, after displaying the hello world, I did this. I inserted some codes here before it will go to this part where I'm going to wait for a keyboard press and then it will exit. This one is wait for a keyboard press and then exit. Actually, I can change this one. Wait, I'll use interrupt 21. What's the code for interrupt 2108? Yan. 08. So run. Then if I'm going to press, still same. See? So we are practicing using the different interrupt call. So this one, what it does is similar to the original one, the interrupt 16, but this one using interrupt 21. This one is keyboard entry without displaying, but if you want to display your keyboard entry, you have to put 01, I think. Yeah, 01. Keyboard with display. This one keyboard entry without display. Okay, but that's not what I want to discuss here. I want to discuss this one. I'm going to show the step by step what happened to the register, since we are talking about the registers. So in our emulator, these are the value of the registers. So don't be alarmed, because when you run a program, probably a previous program have used the register, so sometimes there are already values here. So in this case, there is already a value for CX. And our registers, these are 16 bits. All of these are 16-bit registers. The X's, you have AX, BX, CX, and DX. Actually, they have EX, AX, EX, FX, GX, but we will not discuss it here. We'll just use the AX, A to D. So these are general purpose registers, and they could be further divided into two for 8-bit 8-bit each. You have AX can be divided into AH and AL. That's why in the program, the sample program, you will see that there are some registers here that's only half the register, only 8-bit. This one, it uses AH. And then you have interrupt 21. You use always AH when you use interrupt 21, because the AH, again, determines what your interrupt 21 is supposed to do. The number there in the AH is called the function call. So here in our example here, you have AH interrupt 21, AH09 interrupt 21, means you have to display a string. AH08 AH08 interrupt 21, it means that you are going to wait for a keyboard entry without displaying it. There's a keyboard entry without displaying it, but the value is saved in AH. You can put H here. You just have to get used to putting H, because it means that you're using hex. Although you can get away with it if you have 0 to 9, because they have the same value with decimal, and hex would have the same value from 0 to 9. But if you want to put 10 there, then you have to specify if it's hex 10 or decimal 10. So if you want to hex 10 or decimal 10, you put 0A. It's equivalent to decimal 10. Anyway, what I'm supposed to do here is to run. Where is it? Yeah. Then you have to single step this one. When you do single step, basically you are trapping. This is one of the trap. We discussed about the trap card. When you do a debug, you single step. See what happens is there. First is it will go to this part. This is what is being executed now. And then there, AH is called, and then interrupt 21. Okay, so let's display. So it will go here. It will go to a certain memory location which we do not know. Better that we do not know. You let interrupt 21 worry about it. So it went to this direction, to this address. This is the address where it went. And then if you're going to do single step again, hey, it will now display from that address. It will get the hello world. Display hello world. Okay, so after hello world, what did it do? Okay, we XOR. So basically when we XOR, you will notice that the value of AX here, when you XOR, will become 0. Let's see. Run single step. See, it becomes 0. Step back. Originally AH is 09 because that's a function call we use here, and then there's a certain value 24 in the AL. AH is 09, AL is 24. Later we will try to trace what happened, or you just trace it yourself. But what we did when we XOR, single step, XOR, there it becomes 0. And then if you're going to XOR BX, but BX is already 0, so no worry. Let's say, but let's put a value here. so that you will see what will happen. You get 0 e e e, oops, 0 e e e e h, so that you will see. No, 0 e d d. You will see where all those. Emulate again. Display again. Press any key. There. It has become 0 0 afterwards. When it will be executed, become 0 0. Oh, step. There. Become 0 0. And then what I did for bx, I loaded this value. Let's see if it will load. There. So higher value EE, lower value DD. EE DD. Then you have to put H to indicate that you are loading hex. Actually, in some emulator, you don't have to put H. If you don't put H, it will be taken as hex. But we just have to follow convention, and you have to get used to putting H there. Okay, so that's what happened. CX, originally it has a value, but we put 0. We're going to 6 step, it also becomes 0. Because if you just put 0, it means that's 0. And then we put again AH9. AH does not have any value here, but if you're going to put AH9, where do you think will it go? Lower or higher? AH or AL? It will go to AH. I already indicated AH. So it will go to AH there, 09. And then what I did is you move AX BX. Basically, this means that your source is BX, your destination is AX, so you are going to copy the value of BX to AX. So your BX is this EED. You will notice later on that AX will become EEDD. Oops. Baliktad ba? Baliktad. A destination is AX, so AX will change the value. BX. There. Next step. So we are loading the value of AX into this memory location. Then AH again. AH08. There, 08 again, the AH. So that's what happens. So now we have learned the step by single step. So when you do single step, what's involved there is the trap flag. But let's try C. It says there that C, this is the last one that I'm going to do. I'm just going to show this to you. I can do this move CX, say 9. Let's fix it. 9H or 9. 9H or 9, the same lang. Then let's say loop start. So let's see what will happen. Emulate, run. Okay, something is wrong. So unli. They always start. Something is wrong with my code. I think I should put the code here. Loop here. The mistake is we loop it to the start, so there is no counter. Your counter should be before the label. So this one will only display 9 pieces, 9 hello world there. So that's the difference. Okay, so it also said that one of the special uses for CX is counter. So here we use it as a loop counter. So what we did is a straight loop. We asked the program to display hello world 9 times. So we loop it. That's why we have the hello world 9 times. Okay. So you might ask why does the hello world automatically go to the next line and align itself? Because of this code, this 0AD, 0A, and 24. That's what it does. Go to the next line. Actually, this two are the ones that you need. 0A and 0A, 0D and 0A. But you need to put 24H there because uh, you are manipulating the memory location. Anyway, so that's it for this lecture. Don't worry, all the other things there that need to be discussed or discussed further by giving examples. I'm going to show example. We'll have more examples, and I'm going to leave some lectures and show it how it's done here in the emulator. Okay, so for that I'll close this one and then I'll show you. Not going to save. No, I make my own code. Okay, so go back here, and this is recommended reading again. So there's this tutorial for assembly language specifically for registers, and then you might also want to read about the architecture itself. So with that, I'd like to thank you for listening. See you again next time.